Thanks for the introduction. As you were told, I'm Ronell Carey. I'm a spectrogeologist and I'm currently employed and have been employed for 8 years by Corescan. Okay, thank you. So we also work with spectra, but a little bit different than what you've seen earlier today. We work with, our source of energy is a normal white light. Can't people hear me? No? Is this better? Okay. So I will start with just a short introduction to the VNIR, or visible near-infrared range, and the SWIR range, about 3 slides, and then go on to things we plan to do with all these beautiful images and how it's applied to mining and metallurgy, and then just a few case studies. So I will not go into detail about our instruments. We will do that tomorrow. For you that can't join the group tomorrow, please give us a call and come and visit any time. So let's kick off. I'm sorry my slides are so busy, but I want to tell you so much. And I couldn't choose who shouldn't be shown. But the first thing that's important to remember is that we actually do not work with elements as such. We identify minerals based on the spectra that it gives us. All minerals, if you shine a light on it, it will absorb at a certain energy because of vibrations that happened in the bonds. And we're just so lucky that all minerals have always the same crystal structure. So their SWIR and visible spectra always look the same. And you can identify it purely on the profile of your spectra and where absorption features occur. So, how to find a little light. At Corescan, we work at Corescan, this is not going to work. At Corescan, we work in the visible and the near-infrared range up to 25,000 nanometers. You can go up, some instruments out there are available in the longer wavelength. The difference is if you work in the SWIR range, which is from 1,350 nanometers to 2,500 nanometers, you work with hydroxyl bonds. If you go longer wavelength, you can work with your silica bonds. So we work with mainly minerals that have hydroxyl in them, so the water-rich alteration minerals. So basically what we look at in the SWIR range is this little vibrations that happened in the bonds. And they're all quite funky and nice to look at. We have started to go into more using the visible. Unfortunately, it is an area in the electromagnetic spectrum that's poorly researched, and specific using crystal field transfer. So the chemists amongst you will all know what I'm talking about when I say crystal field transfer. But basically, all minerals are built out of tetraeders and octaeders. And in the center, they will have a metal which is positively loaded. And then they have ligands attached to them, either as tetraeder shape or octaeder. And because of the dislike between the ligands and the metal electrons, you get a split in your electron of the metal. And that happens at a specific wavelength where it will absorb energy from the light as well. So we can use this region if we are careful, and we can map things like autopyroxene, clinopyroxene, and olivines as well, but not without confirmation. So we will suggest this is what you have, and it's then taken another method to confirm that. In the SWIR region, which is just this tiny little bit here, is where all these vibrations take place. It's bending and stretches that happen, and depending how these things bend and stretch. It absorbs at a certain wavelength position, and that helps us to identify the minerals. And we can do that quite accurately and precisely and continuously with the same accuracy. So after all of that waffle, what does it actually look like? Here's an example of a spectrum of white mica. The shape or the profile of the spectrum will always look like this. What will change is the positions of these things. We call these things absorption features. Depending on the composition of the white mica, these positions can shift. If it shifts towards 2500 nanometers, we say it goes long. If it goes the other way, it goes short. Simple as that. It will always have a 1400 feature as well. And here's just a little explanation of which of those vibrations cause these different absorption features. So what we actually, if we look at the crystal structure itself, what we're looking at are these water hydroxyl bonds, sorry, not water, hydroxyl in the crystal structure just here, and they bond into aluminum and white mica. So that's what we look at every day with our data. We will show you how the system works and everything tomorrow and give you more details and specifications. One of the great advantages of working with SWIR data is we can actually tell changes in composition of a specific minerals. Now there's a few minerals we can do it with. The one mostly used is white mica, so we can tell you if you have paragonite, muscovite or phengite. Lately we started to identify white micas with weird compositions as well. The one that we really have a problem with is lithium. We battle to identify the lithium rich and separate that from other white micas. So it all happens because we can do that because this little change in the wavelength position. And that wavelength position change depending on which elements you have surrounding your hydroxyl in the crystal structure. And the general rule is the bigger the atom that sits around your hydroxyl, the longer the wavelength, and then shorter. It basically works when you have big atoms, there's not much space for vibrations to take place, so the frequencies are low, less energy. If the atoms are small, there's a lot of space to vibrate, higher frequencies, more energy, shorter wavelengths. In general, we used a periodic table as well, and as you go, it just tells you how the wavelengths change if you change things in your crystal structure. So this is actually an important advantage of using light spectroscopy. At the moment, I do not know of any other method that can do it as successfully and as easily as light spectroscopy. I may be wrong, and you will probably tell me that later. But okay. So, how can I do this? I can talk in this and look where I'm showing. There you go. Trying to find the definition of a spectrometer on Dr. Google is just absolutely impossible to understand what it tells you. So I've just put this little slide together to tell you how we work. You need a light source, and it has to be a white light. So we use quartz halogen light. You shine it on your core, and then we measure what comes back. So we will know exactly how much energy or how much light photon energy goes in, and then we measure what comes back. We split that light that comes back pretty much the same as what you do with visible light. We just work now further in a longer wavelength range. We split that light into its different components or bands. At the moment, we split our light that comes back into 512 bands, and it gets detected by an array of detectors, and the width that we can scan is dependent on how many of these detectors we have in a row. At the moment we have 100, so we can scan 5 centimeters at half a millimeter resolution. And each one of these will give out a spectrum then. Of course, there's pre-processing and things that needs to happen, but that's not interesting stuff anyway. So as the light moves forward, it scans the next line, and you build up what's named hyperspectral cube that looks like that. So in this direction is all your spectra, and this is your spatial direction. And this then goes into data storage. And I know many people mentioned this morning about big data. This is big data. When we have less than 12 terabyte, we start to panic. We know we don't have enough space. We need, yeah, it's big data. Just a little bit on how we process. We start off with our hyperspectral cube. From that cube, we will then create a project-specific library. So we will go through the data, and we have various ways to identify areas that look different than other areas that which indicate different minerals. We create a project-specific library, and then we put matching algorithms together for every spectra in our library. And we identify things in that algorithm, like where we want the absorption feature to be, how wide we want it to be. If we want to work with ratios, we can work with ratios. We can exclude, we can say you do not have absorption feature in this range. We can do all sorts of weird and wonderful things. There's many ways to get your minerals out of a hyperspectral cube. This is just one way, and this is the way we prefer to do it. So what then happens is our software, which is developed in-house, will match every pixel to every library entry. And as a result, you will get out a binary file for every mineral in there. And it's just values telling how well it matches according to your algorithm. The next step is we color code it, just because we see better in color. And then we apply a threshold, saying that everything below a certain threshold is not that mineral, and everything above that threshold is that mineral. And what we do then in the end is we assign colors to every mineral, different colors, and we add them all together to create a class map. So every one of these different colors are imaginary minerals in this example. And then right at the end, we go and we actually count how many pixels are mapped to a certain mineral. So in this example, there's 20 pixels, and my size of my scanned area is 121 pixels. And this value then goes out as a CSV file. The interval size is totally dependent on what the geologists need in the field. We can change it, the computer does it, so we don't really care. Okay, that's a quick introduction to what we do and our science. Now, in short, when you work with our sort of data, you provide two things. You provide images, and you provide numerical mineral logs. These are the things that all the geochemists want, and all the modelers want, and these are the things that geologists want. So, how can we use the images, or how do we use the images at the moment? Currently, we have 5 projects where we have these spectrometers sitting in a big drill-out projects. The core gets received from the drillers. This is our little instrument. It comes in a container. It gets scanned by operators that we train. The data gets stored on external drives, and then it gets couriered back to Perth. All processing gets done in Perth. And we can immediately upload to the field the results, and the geologists use it within 24 hours of drilling to do their logging, given that the core is dry when we receive it. If the core is wet, we need to wait for that core to dry. Water influences our technology. Okay, so here's just an example when I so confidently told you about how we can show you the chemistry variations in different minerals. So this is just a little vein of white mica, and right in the center it has paragonite, and as it goes out to the end it goes more muscovitic in this example here. We can also tell you something about the crystallinity. In this vein is highly crystalline, and towards the margins of the vein it becomes less crystalline, which is important too if you want to work with temperatures and the evolution of your ore body deposit. Other minerals that we can do this sort of thing for you includes alunite, epidote, jarosite, chlorite. We are working on doing the same for tourmalines as well as amphiboles. We don't have all the information yet available. We're working actually with our tourmalines with codes at the moment, and it looks very, very exciting. Other things that geologists use the images for is to put the vein evolution to the side, which is a major thing for people working on porphyry, essentially. It's the evolution of the veins and which veins came first and so on. Oh. Go back. So this is just a little example. Where in brown here is tourmaline, and you can see there's a little alunite vein just cutting through it, giving you a little indication that tourmaline came first and then alunite after that. It also can give you a little microstructure information. You can see that in your mineral maps. We call these things mineral maps, by the way. So the geologists can use all of these to determine the vein evolution in the porphyries. That's all fine and good, but we can't expect of our geologists to sit and go and look through hundreds of thousands of meters of images to do their vein analysis. So at the moment we're working, and we have been for a while, working on a way to put veins into numbers, and we find that computers are amazingly stupid in identifying veins. This is just a small example. Once we identify where the center of the vein is, we can vectorize it, and once we have it in a vector, we can actually give orientation, dip and strike if we have full core and we have an area line. So we're still trying to develop this. As you can see, as soon as it becomes a bit complicated, the algorithm at the moment falls apart a little bit. Okay. We've learned over the years that we're very happy to help the core loggers to log their core, and it's extremely useful. But we find that it has become more and more used by metallurgists, as it's extremely important to know your minerals when you develop your plants and process your ore. So at the moment we develop into assisting metallurgists more and more rather than exploration geologists. And not that we're not looking at the exploration geologists. We think we have provided them with a good set of tools to do the logging at the moment. So it's important to know if something is pervasive, if it's a vein. It's important to know grain sizes and things like that when you build your plant. So we're trying to put all of these things in numbers. And this is just a small example we did a while ago. We were given broken core. It doesn't have to be broken. As long as you have your mineral maps and you can see the grain edges, you can actually do this sort of thing. You can identify the outline of each grain, and once you do that, you can vectorize. And once you have a vector, you can do all sorts of things mathematically. Like calculate the area, the perimeter, if it's elongated, and all sorts of things. Thank Somebody else this morning also talked about RQD and how important that is. We're working at the moment with a mining company trying to automate all of this. The biggest problem is trying to teach our geologists to use the same marker on all their core and to use as limited as possible markers on core, because those markers do have spectra and we can't sometimes see the minerals through them. So this is one of our current developments, and we hope to push this off very soon, and we can see huge applications for that in mining. We can do this because we have a laser profiler as well to our system, so we have like a DTM that we create of the core, so we can automatically identify the breaks. At the moment, it's just to get the orientation lines out now. We're totally integrated with Acquire. So if you bring up your Acquire database and you have our data, you can display all the images together with your other data that you have. The numerical values you can take into your 3D modeling, and it's often done for that, and you can do enveloping and all sorts of things that you want to do. So the first thing we find, of course, now is that the amount of data we provide is sometimes overwhelming. And the only way really to make it less is to go into machine learning. So at the moment, the only thing we do at the moment with machine learning is trying to cluster things so that we can give mineral, the word escaped me. So this is just an example where we have about 50 minerals, and we downgraded to about 8 or 9 groups of minerals. The next step is then to feed this into the machine learning or neural networking to start predicting where, say, your gold will occur, and do all sorts of fancy things like that. Just a quick few slides of case studies. This is REGOLITH and Carey. We've been working on this project now for about 5 years. All their core gets scanned by us. This is the list of their minerals. Up here, we provide this on all the data we give them. It's a very complex little system with loads of different deposit types. And what this geologist did, he just brought in all these images into our public-based network software, which is called CoreShed. And he just, by eye, divided into different zones. We did a nickel laterite study, and where we used the spectrum trying to subdivide the nickel laterite into its various zones, and it worked fairly successful in this area. And finally, we all know why mineralogy is important. I don't have to go through the list. What we also try to do is to bring core back to the office. I don't know if any of you are exploration geologists. You end up in an office and you miss your core dearly. This helps me to see core again. And yes, I just want to thank everybody at Corescan who assisted in doing this work. I had a great team behind this. Any mistakes, yes, mine or theirs. We have a team of geologists, some engineers, IT people, operators that all assist and help putting this presentation together for you. And thank you for your time. And I didn't get the red one.
The obvious question, of course, and you brought it up yourself, is the overwhelming data density. The company that I used to work for was involved in a very early experiment with Corescan. We generated a huge amount of data, and the question is, what do you do with huge amount of data? So do you have any pearls of wisdom about how to reduce this volumes of data to interpretable results?
So until very recently, we worked with a little company in Brisbane called Solve to do machine learning, trying to cluster things together and to reduce 50 minerals to, say, 8 mineral combinations. we've now actually employed our own programmer because we want to enhance and progress and do this quicker. We can't wait for another company to do it for us. So yes, we're definitely trying and working with as many as possible people, trying to, in a sensible way, reduce the amount of data you get. Still useful. And it is a problem, you're quite right. It's overwhelming when a geologist gets his drill hole and there's 50 minerals. And now he has to go and log against 50 minerals. He very quickly lose interest. So yes, it's a very good point. I'm unhappy if my project don't have 60 minerals, but that's just by and by.